Well, of course, thank you all the organizers for the opportunity to present this work. This is essentially a work on quantum annealing and many of the open quantum systems. So I want to essentially flash out here the collaboration. So this is a large collaboration with the group of Hidetoshi Nishimori and Daniel Lidar, and also my postdoc Fernando Javier Gomez Ruiz. And the idea is you are given a black box and you want to know how it performs, what it actually does. And of course, one of the best ways is just take a paradigm, something that you understand very well, such as the dynamics of a phase transition, in particular for kink formation, and test it and see to what extent a quantum annealer behaves according to the theoretical predictions. We will do something beyond, but this was the starting motivation for the project. And the paradigm we wanted to test is that of the finite time crossing of a continuous phase transition, in which, for instance, if you drive a paramagnet to a ferromagnetic phase in finite time tau q, then you don't get only a single domain. Your sample will have a mosaic of different domains, and at the interface between domains, you will get topological defects. And there's the well-known Kibble-Surek mechanism that actually estimates what's the length scale for these domains, and it follows universal power law with the Quentz time tau q with a power law exponent which is universal. Yeah, so it's the combination of the nu being the correlation length critical exponent and Z the dynamic critical exponent. So this is well known. This essentially was put forward in a classical context, and there were beautiful works in 2005 that took the very simple one-dimensional transverse field quantum missing chain, and this is integrable model that can be written in terms of free fermions. And for this model, there's an operator that counts the number of kinks, the number of spin misalignments, and it also happens to take a very simple form in the fermionic length, which is just the sum of occupation numbers. And studies by Anatoly Polkovnikov in the audience and others in 2005, 2003, actually, starting earlier, consider the driving of the phase transition in finite time by changing the magnetic field G in this time scale tau q, and so that the expectation value of the kink number operator in the final non-equilibrium state follows this expression, this power law with the tau q, with one, with a square root, which essentially agrees with the Kibble-Surek prediction for nu and Z equal to 1, which is the critical exponent, so the isolated transverse field quantum missing chain. By now, we know beyond these works that the Kibble-Surek mechanism actually applies very broadly, have been tested as well in non-integrable systems, and there are many experiments that are consistent with it. Early ideas were introduced in a cosmological setting, but we have seen a flow to other fields, condensed matter, superconductors, soft condensed matter, quantum simulators, and more recently quantum annealing, which is the part in which I want to focus. Well, I want to also couch on something which goes beyond Kibble-Surek mechanism, and this is something which resonates with some of the theories in transport, in particular the full counting statistics and the counting of electrons passing through a point contact. So I want to study not only the average number of kinks, but also introduce the probability distribution to have a well-defined number of kinks in a sample. Yeah? So this is a prediction that goes in principle beyond Kibble-Surek mechanism that is restricted to the mean number, to the average. And I want to characterize the full distribution, which is depicted here. So this is based on theory back to 2008 and some recent progress. So the setup is going to be exactly the same. I take the transverse field model, so it's the same as in the 2005 studies. I look at the same operator, the kink number operator, but instead of looking at the expectation value, I just look at full counting statistics, which tells me the probability for this operator, the kink number operator, to have a well-defined eigenvalue, lowercase n. Yeah? And this angular bracket is just the trace over the non-equilibrium density matrix in the final state after I have crossed the phase transition. In principle, I'm considering so far everything for the system in isolation, evolving under Hamiltonian dynamics, unitary evolution. And it turns out that, maybe you don't like this Kronecker delta. It's, if the spectrum is pointwise discrete, this will be a Kronecker delta, otherwise will be a Dirac delta. We can, this is a probability distribution, so we can Fourier transform it and introduce the characteristic function that's p tilde of theta, where theta is the conjugate variable to the kink number. Yeah? And, we are in a lucky situation where, here the characteristic function is just the expectation value of, the exponential of a Hermitian operator, which typically we know how to deal with. And in particular, it's even simpler because remember that the kink number operator is the sum of the occupation numbers. So, so in this case, there's this simplification in which I can exactly write the characteristic function as the product over essentially independent classical discrete random variables. Yes, so I can, I'm driving the phase transition of a quantum missing chain, and I can think of it or describe it in terms of a set of independent random classical events in which the probability of success, which the probability to create a pair of kinks, pk, is computed quantum mechanically through the Landau-Zener formula. And with that probability, I excite a pair of kinks. With 1 minus pk, I have no kinks form. Yeah? And I do this for n half modes, and essentially this sets the full counting statistics in this setting. Right. So with this knowledge, you actually already know everything. Essentially, you go to a textbook in probability theory. You can as well identify the kind of distribution you have. This is what is called a Poisson binomial distribution. And I'm going to mention some of the main features. This is essentially just a summary of what I said. I'm describing the Ising chain, but I can think of it in terms of coin tossing for different kind of biased coins and just estimate the probabilities with Landau-Zener formula. Now I can plot this distribution, and this is how it looks like. So if I go very fast, my distribution is big at high kink numbers, and it's very broad. If I drive the system more slowly through the phase transition, then the average kink number gets reduced because we are approaching the adiabatic limit, and also the distribution shrinks. It becomes more peak, and the variance decreases. Now, for quench times slow enough, then the distribution becomes asymmetric because, of course, the kink number can only be 0, 1, 2, 3, 4. So, once you have a finite probability of populating no kinks at all, so that's like you get a perfect ferromagnet with no kinks, then the distribution is asymmetric. But what you see on top of the histograms are actually fits to a Gaussian distribution that otherwise, away from this very of the adiabatic limit, work very well. Yeah, and these Gaussian fits are essentially derived theoretically by, in an approximation I mentioned later, but essentially have the feature that, of course, the kink number is thick at the prediction by Kibble-Schreck, and the variance is linear, is proportional to the mean. It's not equal to the mean, so it's not a Poissonian distribution. There's a factor of 6 over pi square. So there's a proportionality factor. Yeah? But otherwise, this Gaussian approximation seems to work pretty well. You may want to do better, and actually, given that you know exactly what's the characteristic function, you can introduce its logarithm, which is the cumulant generating function, and use the formal standard expansion to generate cumulants kappa q. So here q is an integer which goes from 1 to infinity, and the first cumulant is the density, the second cumulant is the variance, and so on. And for the cumulant generating function, you can find a closed integral expression, which is there in the center of the slide, in terms of the quench time tau q. And it turns out that tau q is long, so near the adiabatic limit, where Kibble-Schreck mechanism is expected to hold. Then this expression simplifies very much. And then you find that the cumulant generating function is proportional to the mean value of kinks predicted by Kibble-Schreck mechanism. Now, if you compare the formal cumulant expansion with this last expression, then you conclude that any cumulant is proportional to the mean density of defects predicted by Kibble-Schreck mechanism. So any cumulant of distribution has now the same universal power of scaling that you expect from Kibble-Schreck mechanism. To solve this more explicitly, let me just solve, for instance, the computation of the first few cumulants. Of course, the first cumulant is just the mean density, or the mean number, which equals to with the Kibble-Schreck prediction. But if you look at the variance, then you see it's proportional, but there's this proportionality factor is smaller than 1, so it's a sub-Poissonian distribution. Higher order cumulants are all non-zero. You can solve that, and I just put here the third cumulant, which again you see is proportional to the mean with some constant coefficient. So the distribution is not Gaussian, really. It's not normal. And there are all these higher order cumulant corrections. Now, to solve all the cumulants scale universally, you can just make a plot. You can compute cumulants explicitly with equations given and solve how they behave as a function of the Quent's time. So we know that the mean decreases. That's the Kibble-Schreck prediction as a power law with the Quent's time. But the variance and the third cumulants follow the same power law scaling up to finite size corrections at very long Quent's times, or very fast Quentzes where Kibble-Schreck does not apply because the Landau-Zener formula fails in this derivation. By now, this was all for the transverse field easy model, but we have put forward, reported a number of works where we provide a much more complete picture that does not rely on interpretability or the solution of the transverse field easy model. We have studied for classical field theories, classical spin systems, the work here based on D-wave, but we have also done works on higher dimensional setting for superconductors in holographic setting, and so on. Yeah. So there's a more broader picture than the one I'm giving here. The prediction is clear. Not only the mean number, all cumulants of the distribution are proportional to the mean, and they therefore inherit the power law scaling with the Quent's time. So let's now go to test this in a quantum annealer. And I just want to mention, I guess, so here my collaborators, so Daniel Lidar, Fernando Javier Gomez Ruiz, and then the group of Nishimori, one of the visits I had a chance to play them. And I want to mention, we were not the first to propose the test of Kibble-Schreck in a quantum annealer. There was this early work from 2018. It was inconclusive. You can read the reports. The machine was too noisy. It was early generation, so not much was learned from it, other than some phenomenology on the dependence on the Quent's time. A more recent experiment was also done embedding a two-dimensional quantum easy model, and this was reported by the Boston University group. And they saw a crossover between a Kibble-Schreck behavior and what is called anti-Kibble-Schreck behavior. But this is the opposite of approaching the adiabatic limit. You try to go more slowly to suppress excitations, but you get more excitations. And this is something that we already predicted in 2016 in this work, where we saw that any classical heating source, such as fluctuations in your magnetic field, can give rise to heating that competes with the decay of excitations predicted by the Kibble-Schreck mechanism. So there's this interplay between heating and Kibble-Schreck dynamics, and that's how you can understand easily this anti-Kibble-Schreck mechanism. But let me move to the work on the that we have done, because we consider exclusively the one-dimensional transverse field easy model. This is the one we embedded in the web machine. Essentially, this is a programmable many-body quantum spin system, so one hops. And we chose two different machines, one at NASA, one at Burnaby. It's likely almost the same machine. Burnaby is known to have a bit lower level of noise. NASA is supposed to be a bit more noisy. This is all what we know. When we change the coefficients, it's not possible just to change the magnetic field as we did before. So here we have two coefficients, A and B. B is the ferromagnetic coupling, or anti-ferromagnetic coupling, and A plays the analog of the magnetic field. And when we change one, we also change the other one, and you see here what's the dependence of the schedule. Yeah? And it turns out that to just get rid of any fabrication of errors of the machines, when we program one given spin chain, we do it in, say, 200 different ways to make sure that we don't pick up any qubits which are faulty. And once we fix one of the embeddings, we collected statistics 1,000 times. So in total, for every annealing time, we have 200,000 realizations, which is pretty high statistics. We also tried something what is called Gates transformation to get rid of some errors. In the end, we did not use it, I just mentioned it. But essentially, we collect data for the mean density of kinks, making the chain ferromagnetic or making it anti-ferromagnetic. And we also try anti-ferromagnetic plus this Gates transformation to see where it made any difference. We have done this for different system sizes. And what we see always is that if the chain is just of 50 spins, there are important finite size effects, and it does not behave nicely or universally. So we essentially will just look at larger spin chains of a few hundred spins, where we see consistent behavior. We are also told by the specifications of the machines that we should not trust the data for over 100 microseconds because error sources are not even well understood there. So we just will focus on the regime of annealing times between essentially 1 and 100 microseconds. And again, error seems to be more pronounced in the ferromagnetic case, so we single out the antiferro as the test case for the study. So we are wrapping the phase transition in a one-dimensional transverse field model in these machines. In two of them, we reproduce the same experiment and we fit power laws. Essentially, what we see is that if we try to get the power law exponent in each of the machines, we find different numbers, different power law exponents. Again, let's forget about the case of L equal 50. Let's just look at the others. In the NASA machine, we have something like 0.2, and in the Burnaby machine, we have something like 0.3, 0.4. Remember that in the isolated transverse field model, the prediction was the square root. So that's an exponent of 1/2, which is essentially inconsistent with any of these data. Yeah, so these are really make us think that these machines are not really mimicking isolated quantum spin chains, but actually they are in some sense open or possibly decoherent. So let's try to sort this out. So we plot the exponent we find in one of the devices, NASA 0.2, the other one 0.34, and the prediction for the quantum Kibble-Surre-Kissing chain in isolation is 1/2. So clearly these are inconsistent. So we have tried a paradigm a usual common test of classicality, which is the so-called spin vector Monte Carlo. And let me just tell you that also is not able to reproduce the results. This I will explain in a bit what this SVMC it is, but essentially the paradigmatic classical model that is proposed to capture the behavior of an annealer is not able to describe experiments. We also have some, to the extent that we also have a theory for quantum open systems that, however, is able to reproduce the range of exponents which is observed, not just this 0.28, but actually a range of them. So from this point of view, one is tempted to conclude that this is the first test of Kibble-Surre mechanism in a many-body open quantum system. And I only leave there a question mark because nothing precludes anyone in the audience or elsewhere to come out at some point with a classical model that captures the same physics. This is always a problem with this. As you can only read the final result, you always there's always a question open where there's some other model that describes the same behavior. But people have tried hard to capture with classical models where this was possibly explained by quantum dynamics, and so far there are 3 negative results. The model that we propose as an open quantum system is very simple. It's a spin boson model where we have coupling of harmonic oscillators, the position of harmonic oscillators to the Pauli set. Pauli set is in the direction that favors ferromagnetic or anti-ferromagnetic order. And just using an ohmic spectral function with a sharp cutoff, this is the model which has already been successfully used to describe some of the features of quantum annealers, building on works from the 90s by Subit and co-workers. It is known that this coupling to a bath in the explicit form quoted here renormalizes the critical exponents, the correlation length, and the dynamic critical exponent without destroying the phase transition. This does not give rise to anti-Kibble-Surre mechanism, as in the Boston University experiments. It does, it just changes the value of nu and Z in a way which is favorable and brings it close to the observed value. To test this more carefully, this was actually done by the group of Sei Suzuki. So there were simulations done to capture finite temperature effects. And what it is observed is that the density of kinks has a plateau value that depends on the temperature. The theory I mentioned here was for 0 temperature, and this is actually the regime in which we focus. So this is the plot in the left, where at 0 temperature, but by changing eta, which enters in the spectral function, you see that we can actually tune the power law. Yeah? So the slope of the density of kinks with the quantity time in a logarithmic scale. So that's the power law exponent. And we can do it interpolating between the value, which is known for the system in isolation. This is the 1/2 to one that corresponds to high dissipation. That will be something like 0.2. So this allows us to, essentially claim that, what we're seeing is kind of 2 cases of dissipative quantum missing chains, one with weaker noise, one with stronger noise. As for the classical model that we consider, maybe this is known to some of you, is so-called spin vector model, spin vector Monte Carlo model. What you do is, you want to describe within classical statistical mechanics a transverse field IC model. So you substitute any of the Pauli matrices by a cosine of theta. You essentially have classical planar rotors instead of quantum spins, and you mimic the lack of commutativity between the different Pauli matrices by making the ferromagnetic to go with the cosine of the angle of the rotor, cosine, and the transverse magnetic field with the sine. So it's a model which has been used recurrently, and there's, however, a problem. Being a Monte Carlo method is unsuited for describing real-time dynamics. But well, this is essentially the best that is out there. We just saw that actually this is not sufficient. We got something qualitative same behavior, but exponents of order 0.48, so close to 1/2, that are not able to reproduce the data. Yeah? I should mention that there are another 2 studies, with one with Lauber dynamics, which is kind of a continuous time Monte Carlo method, also does not reproduce the data. Yuki Bando and Hidetoshi Nishimori did simulated annealing and also conclude that this is not able to reproduce the data observed. Yeah? So this is the effort so far to test whether there's a possible classical explanation. So with this, essentially we see that in this sense is this first test of Kibble-Surek in an open quantum system. Now we can go beyond Kibble-Surek by looking at the kink number distribution. And
Adolfo, I'm sorry to interrupt. So the time is up. So if you could please summarize within the next couple of minutes.
Sure.
We have time for this.
Yes.
Yeah, thanks.
Yeah. I do that. So we can look at the full counting statistics, which goes beyond, and that we saw before that it was well described by Gaussian fits, which match very well. We can look at the scaling of the cumulants due to the high statistics. We can see them; they follow beautiful power laws, and the cumulant ratios are constant. Yeah? And these are the observed constant values are in agreement with the theory. So this is essentially also, I would say, the first test of physics beyond Kibble-Surek mechanism in any many-body system, whether classical or quantum or not. Yeah? So I guess this is the second main point of the talk. Yeah. So we also test that the behavior is non-thermal. So let me skip the part and just conclude. So we have reported the first test of Kibble-Surek in an open quantum system with the caveats made, and we have provided the first test of going beyond Kibble-Surek by looking at the full continuous statistics of defects in a many-body system. So yeah, thank you all for your attention.
Okay, thank you. So we have plenty of time now for discussions or questions. Anatoly?
Hi, Adolfo. Thanks for that.
Anatoly.
Some time ago, I worked with Victor Gurali, Alex Antland on sort of similar problem, but for James Cummings model. And in the slow limit, we also found like very interesting statistics, like Gumbel distribution, like totally asymmetric, but still universal. I just wonder if you saw anything like that, or it's totally different?
So that's interesting because I know your work on large deviation theory on, I think it was on work statistics, not on kink statistics. Or am I mistaken?
It's the same. It's basically you have like a photon mode which is coupled to all spins, so it's like all-to-all model. And then as you drive, you count number of photons, but it's the same. It's in a way.
Right. So I may not be familiar with this work specifically. I have others in mind, and also by Alessandro Silva and so on. So when we look at not in this study, but we look also at the vortex number statistics in a holographic superconductor, and there we did we look at the large deviation theory and did find the Gumbel distribution.
I see.
Yeah. So indeed, there's a strong connection. So this is the kind of questions you can pose. Not only what's the mean value, what's the variance. You can also say what are the tails of the distribution, or what the probabilities to have large deviations. Yeah. So I guess this is the kind of new language that we're pushing forward. But yeah. Thanks for your pointing out this study. Yeah.
Okay. Other questions? So maybe I can ask a question. So that was a study for the 1DK. So has there been other studies for other models like higher dimensions?
Yeah, so we have only done one so far, which is for a 2-dimensional superconductor, 2+1, but let's say It's in a holographic setting, so that requires very heavy numerics because it's, but never mind. So there has only been one study for a two-dimensional superconductor where the defects are again point-like, are vortices. So, I guess it's open to see what happens. The theory we have, which is generic, I mentioned we did for field theory as well. It's only for point-like defects. We have not extended to, domain walls or, other kind of topological defects. So we have tests for point-like defects in more than one dimension, but not for other kind of topological defects such as domain walls. So yes, two-dimensional easy model, even classical, will be an interesting study.
Okay. Other questions? Well, if there are no other questions, then let's thank Adolfo again for this nice talk.
Thank you for your attention.
And thank you. Let's thank also all the speakers. So this concludes our first session today. And then we will be meeting again in an hour. Thank you.